So series is one kind of connection. The other kind of connection we frequently use is a parallel connection. In parallel, we can think of where two capacitors are connected top to top and bottom to bottom. So in the circuit diagram, the top of C1 comes out here, top of C2 comes out here, and they could meet right here. C3 comes out, C2 comes out. So all of these tops are connected by a single ideal wire. All of these bottoms are connected by a single ideal wire. What happens in practice when we connect a circuit is that a wire comes out of C1 and goes into the battery. A wire comes out of C2 and goes into the battery. So C1 is connected directly to the battery. That means the potential across C1 will be the same as the battery. C2 will also be plugged in right on top of C1 into the battery. So C1 is connected to the battery. That means it'll have the same potential as the battery. Then likewise for C3, wires will come out of that one and go straight into the battery. Because it's straight into the battery, it will have the same potential as the battery. Okay, so what we're getting at here is that when things are connected in parallel, top to top and bottom to bottom, they all have the same potential. So capacitors in parallel all have same potential. So series has same charge, parallel has same potential. So they all have the same potential, delta V. So delta V1 here equals delta is epsilon, the same delta V as the battery. So we might say delta V instead of epsilon. For C2, delta V2 is delta V, same as the battery. C3, delta V3 equals delta V. What happens to the charge? That's important to think about. So this time, when a charge leaves the battery, so the positive charge will come out of the top terminal, it will flow along, and at this point it's going to hit a branch. It has a choice. Either it will come down to C1 or it will go forward. If it gets to here, it has another choice where it will either come down to C2 or it will carry forward and go to C3. So the charges will split. So the charge, every charge that comes out of the battery will either go on to C1 or C2 or C3. So the charge divides over the three capacitors. So if we wanted to write down an equation that says that the net charge leaving the battery is divided over the three capacitors, we would see that the net charge Q was Q1 plus Q2 plus Q3. We know that the charge on a capacitor is given by the capacitance times its potential. The potential on C1 is delta V. Charge Q2 will be C2 times delta V2, which is just delta V, likewise plus C3 times delta V. So that's for the net charge that comes out of the battery. It gets all split. Like we did with the series circuit, we can draw an equivalent circuit, which means that, so equivalent circuit, we remove these three capacitors, we put in one single capacitor, and when connected to the same battery, it will give the same net charge. So this will carry charge Q, and the potential across the plates will be delta V. So this equivalent circuit will have a capacitor C equivalent, there will be delta V between the plates, and it will have net charge Q. So we can say that C equivalent will be Q divided by delta V, where the net charge Q will be C equivalent times delta V. Let's put that over here. C equivalent times delta V. We might notice here that we have a delta V in every term on both sides, so we can divide through by delta V, and we see that we get the result C equivalent equals C1 plus C2 plus C3, and if we had more capacitors, we would just keep adding them. So this is our expression to find equivalent capacitance for a set of capacitors connected in parallel. Again, if you did physics or circuits in high school, you might notice that this equation looks similar to resistors in series, so make sure you're not getting those confused. So there's our capacitors connected in parallel. Let's do an example. So in our example, we've got a battery with potential 9 volts. We've got 3 capacitors. Let's call them C1, C2, and C3. And the question we're asked is to find the charge on and the potential across each capacitor if delta V is 9 volts. So these capacitors are all connected in parallel. And we see that because they're all connected top to top and bottom to bottom. If they're all connected in parallel, they all have the same potential. So the first answer is delta V1 equals delta V2 equals delta V3 equals delta V equals 9 volts. Okay, pretty easy. If they're in parallel, they have the same potential. Okay, for our charge, Q1 is C1 times delta V. 12 times 10 to the minus 12 farads times 9 volts to give us 108 times 10 to the minus 12 coulombs. Q2 is C2 times delta V, 22.1 times 10 to the minus 12 farads times 9 volts to give us 199 times 10 to the minus 12 coulombs. Q3 equals C3 times delta V. C3 is 57.9 times 10 to the minus 12 farads. Multiply that by the potential difference, 9 volts, and we get 521 times 10 to the minus 12 coulombs. Okay, so that takes care of our straightforward connections.